The second lecture in my course. Last time we defined stratified spaces, we defined pseudomanifolds, and today I want to talk about intersection homology. Now there are several ways to introduce intersection homology. You can either do it using sheaf theory, or you can use singular chains, or you can use piecewise linear chains, and so on. Now, later in the course, I want to take the sheaf theoretic point of view, but today, I think initially, if you've never seen this before, it is better to give some geometric motivation for the definition of intersection homology, rather than start with, well, the relatively abstract sheaf theoretic description that one is led to later, and which is motivated by chain theoretic properties of a cone, intersection chains on a cone. So that's the route I want to take. I will introduce intersection homology using piecewise linear chains. So, but as I said, we have to therefore pick carefully a chain model, because there are various chain models, also some using finite chains, some using infinite chains in the literature, so one has to say carefully what one means. So let me just talk about our chain model. So let X be a PL space. That means we have a class of triangulations T, locally finite. Now suppose T is a triangulation coming from this collection. Then I can look at functions, say Xi, from oriented I-dimensional simplices in T to the integers or any other coefficient group that you like. So we might also consider later, especially, the real numbers, for example. And we consider the collection of all these, however, noting, of course, that what we want is, if I reverse the orientation of a simplex, which I'll write as minus sigma, then the function should also change sign. So this is what we stipulate. And this is an abelian group, and we call it the simplicial I-chains in X with respect to the triangulation T. Now, of course, if you change the triangulation, so if T prime now is a subdivision, then evidently there is a canonical map to the chains with respect to the subdivided triangulation, because you can simply subdivide the chain. I mean, if you suppose the chain assigns the number 5 to this simplex, right? Now, if the simplex gets subdivided somehow, then you simply assign 5 to all of these, right? So there's an obvious way to make a map. Notice also that there is something called the support of a chain, which is just the union of all closed simplices where the chain has non-zero value. So I'll write it with these bars, bar Xi. So that's a support. That's a subcomplex, a sub-PL space of X. And now, with respect to this system of maps, I can then take the colimit. And I call this Ci of X. And these are the PL chains. This is the abelian group of PL chains on X. What is very important here is I'm not placing the restriction on on this map that it should be non-zero only on finitely many simplices. I do not impose this. So in other words, what we're talking about here are possibly infinite chains on X. Now this defines a chain complex. There's the boundary map as usual in simplicial for simplicial chains. So it becomes a chain complex, and then I can take homology of that complex. And this will be by definition the homology of X. But again, be careful, this is not the ordinary homology, right? This is not a homotopy invariant because I'm using infinite chains. So this is sometimes called in the literature Borel-Moore homology. But I don't want to decorate it with BM or something all the time, so I call that HI, Borel-Moore homology. Now, of course, you could use finite chains here as well, and then you would get the ordinary homology. And you have a choice. You can base intersection homology on this model, on the Borel-Moore homology, or on finite chains, and both have their particular applications. So I'm using, we use infinite chains here because we will later need restrictions. As follows. If you have an open subset in X, I would like to have a restriction map from CIX to CIU. Now, obviously, if you work with finite chains, there is no such map, right? You cannot just restrict it to an open subset. It will not be representable anymore by a finite chain on the open subset. But I need this because later on I also want, as I said, to give the sheaf theoretic point of view, and this is the kind of sheaf property, right? Sheaves have restriction maps to smaller open subsets. That's it's the defining property of what a sheaf is. And so for that reason, I use infinite chains primarily. Yes?
So what do you is the meaning of the 5 in this triangle?
This is the value of the chain.
Okay.
It's a function from simplices to Z. So it assigns to every simplex of a particular dimension a number.
Okay.
And so it's maybe 5. Okay, so that's the reason for using infinite chains. Also, I mean, if you want to relate this to ordinary homology, if you don't like this and you would like to actually see what this is in terms of ordinary homology, then you could think of it as follows. If X is locally finite, locally compact, so that you have a one-point compactification, then this kind of homology, you may think of it as the ordinary homology of the one-point compactification rel this point. So in other words, of course, if X is itself compact, then there is no difference. So then, right, both homology theories coincide. But if X is not compact, then it's very different. For example, H0 of the real line is 0. In ordinary homology, the point would be a generator, but here it isn't because it bounds. Because if you take any point, you can just take that infinite chain and it bounds that chain. Therefore, the homology is 0 in degree 0. On the other hand, the first homology of the real line, or the first Borel-Moore homology, is Z, because there is a fundamental class, if you will. In other words, you could just make the sum you could triangulate it like this and then take the sum of all these simplices with value 1, let's say, and that's the generator. That doesn't bound anything, and so it's, that's the generator here. Okay, so that's how this works. From this, you also see that this is not a homotopy invariant, obviously. It's like cohomology with compact supports in a way. Okay, so that is the chain model I want to work with. Next, I want to discuss briefly a theorem of McCrory. I want to try to make the definition of intersection chains appear as natural as possible. And therefore, one should perhaps analyze in more detail what actually goes wrong with Poincare duality. We have seen that something goes wrong, but we don't understand exactly yet what it really is that fails here with this cap product with the fundamental class. So I want to analyze this in somewhat more deeply. So before I do that, we should maybe define what an orientable pseudomanifold is. It's not quite evident. You can't do it in terms of a tangent bundle and so on. But you can simply say the following. A PL pseudomanifold Xn is orientable if the n simplices can be oriented in such a way, so each one individually, if you're able to, for each n simplex, pick an orientation in such a way that a chain which assigns 1 to each of these now oriented simplices is a cycle, so has no boundary. Right? So for example, if you take the Klein bottle and you try to do this for the two simplices, you can play around with it and you will see that it can never work. And here, the lower dimensional simplices don't play a role. And so this is a definition of orientability which is perfectly valid even in the case of a pseudomanifold. Now, in such a case, an orientation is, of course, a choice of such orientations of these ends, right? So the choice of such a cycle is then an orientation. And of course, the cycle defines an element in the nth homology of X, and that is called the fundamental class. So the point is, orientable pseudomanifolds have a fundamental class in the top homology, just as manifolds do. And for this, I don't need to assume that X is compact. For example, you see this example here. Now, let's define transverse chains. So if I have a chain Xi of dimension I say Xi is transverse, and perhaps I'll just use this symbol to abbreviate this, the usual symbol for transversality. So I take the support and I intersect with a stratum of codimension K, and I say the dimension of that intersection should be no more than I. Now, what should it be in the transverse case from linear algebra, right? When do two vector spaces intersect transversely? Well, you take the sum of the dimensions of the subspaces, and then you subtract the dimension of the ambient space. So this is nothing else than I minus k. So if this dimension is no more than I minus k, I will say, and this is true for all k, then I say the chain is transverse, or more precisely transverse to the strata, we could say. And I can make it, using these as my chains, I can make a chain complex out of these by saying I look at all chains such that Xi is transverse and the boundary of Xi is also transverse. So then this becomes a chain complex because I've required the condition explicitly also for the boundary, and I call this IC 0 I of x. Now secretly, this already stands for intersection chains, but I'm not saying it yet, right? So these are just the transverse chains. Okay. Now let's think about the following lemma. Yeah, so this leads, of course, to homology groups, which I call IH0, I of x. That's just the homology of that chain complex, of course. So I want to think about cap product with the fundamental class. So if I go from the cohomology of x to the homology, via cap product with x, and here maybe let's take x to be compact. I mean, really here I want to emphasize the singularity structure. I mean, that's sort of the important aspect here. So, and here we have this third set of groups. Of transverse chains. Notice that there is a canonical inclusion map from this complex to all chains, of course. It's a subchain complex, and that inclusion induces, of course, a canonical map here. The claim of the lemma is that this map actually factors through this. Actually, the image lands naturally in that group rather than this one. So it's much better actually to think of the image of cap product with the fundamental class to think of as being a class in here rather than a class in here. Now, why is this true? So the proof, or the reason for this is the map given by capping with the fundamental class sends the characteristic function of a simplex to the dual block of that simplex Of course, you have to pass to the first barycentric subdivision, but that's all okay because we defined these to be the co-limit over all triangulations. So we can do that. The dual block of that simplex, and now we just observe, note that the dual block and its boundary are transverse. And that's the proof. So actually, this lands in here. Now McCrory's theorem then says the following. Yeah. Yeah. Sorry, where?
When you define IC,
here,
guess the notation is O over 9.
It's a little zero. And it will eventually be what's called a perversity in intersection homology theory. And this will then correspond to the zero perversity. But I'll come to this in a second. So it's a little zero with a bar above it.
So when you write h upper n minus I, this is the chain complex, the homology of the chain complex generated by finite linear combination.
Right. I mean, here, since I said X is compact, you might even take finite chains here, right? So here you should not get confused about finite and infinite chains. Let's just say we have a compact, but that's why I emphasized, let's just take X to be compact so that we are not distracted by this. And then you can just take ordinary finite chains and ordinary cohomology the way you're used to. And everything is correct. So McCrory's theorem then is the following. If X is normal, so what does normal mean? Normal simply means, I think I said it yesterday briefly already, at least during the problem session, means that the links are all connected. Okay, so normal means links connected. So if this is true, so for example, if you have the pinched torus, the theorem doesn't apply because the link of this point consists of the disjoint union of these two circles, and therefore the link is not connected here. So the pinched torus is not a normal space. But if X is normal, then if we focus on that map, right, so the statement is that there exists this factorization. Now, if we focus on that map, into the group of transverse chains, then this is an isomorphism. So this is now rather fascinating because now we have a much deeper understanding of what goes wrong with Poincare duality. Poincare duality says, and we've seen this in examples, that this map is not an isomorphism. But now we have this factorization, and at least if X is normal, we are being told that this map is an isomorphism. Therefore, it cannot be that this map is an isomorphism. So what's responsible for ruining Poincare duality is actually not the cap product with the fundamental class, but it's that this inclusion, the inclusion of transverse chains into all chains, is not an isomorphism. That's really what goes wrong with singular spaces, with Poincare duality for singular spaces. So the theorem implies now that for X singular, this inclusion map this map induced by the inclusion is generally not an isomorphism. Right? By the way, the assumption of normality is not a big one because one can always normalize a space. There is a canonical process which assigns to a space that's not normal a normal pseudo-variety. So in essence, one can always assume that, and it's in that sense, this is not a very special class of spaces, the normal ones. That's sort of the general case almost, right? Okay. Is generally not an isomorphism. And so this means really the following. It means that the singularities prevent us from moving any chain to a chain which is transverse to the strata. So it's a fundamental failure of transversality that occurs here. If I could, given an arbitrary chain, if I could invent some clever moves that make it, some perturbations that make it transverse to the strata, then this would be an isomorphism, right? And then the composition would be an isomorphism. So so we conclude in a singular space chains cannot generally be made transverse to the strata. So that's the lesson to be learned here. And this, in a way, suggests what you might do to repair this, because perhaps you want to allow a certain error. I mean, to understand, we are now reduced to understanding why this map is not an isomorphism. But to measure how far a transverse chain is from an arbitrary chain, we could introduce a parameter that allows successively bigger errors in this estimate until when the error is very large, you don't place any restriction on the map anymore, and then you have this group, right? And then if you have filtered it through all of these parameters, you get a very detailed understanding of where exactly Poincare duality fails in this long factorization of, well, of this map or this map, right? And this is what Goreski and MacPherson have done, right? So now for intersection homology, the basic idea due to Goreski and MacPherson is specify an allowable deviation from transversality, and they termed this deviation perversity. Right? The deviation from full transversality is termed a perversity function. So let me now formally define what a perversity is. A perversity is a function p bar from the set of integers 2, 3, and so on to the non-negative integers with the following conditions. At 2, the function should be 0, and then there is a moderate growth condition. It cannot decrease. It must always grow at each step or stay the same, but if it grows, it can grow at most by 1. So in other words, pk plus 1 is less than or equal. So it's at most, it increases at most by 1, but it never decreases. Okay, so such a function is called a perversity. Now these conditions are not entirely clear at this moment, but they are responsible ultimately for making this a topological invariant and independent of the stratification. That's why one adopts these. Good. So there are some examples of perversities that occur all the time. So we have already seen one, the zero perversity, because if I just take the sequence consisting all of zeros, then that's the case that I just discussed with these transverse chains. Now, on the other hand, at the other extreme, there is something called the top perversity, T, which is the fastest growing sequence allowed under these conditions. So to 2, it must assign 0, that's prescribed, but then the fastest it can grow is at each step it increases by 1. So the sequence is 0, 1, 2, 3, and so on. That's called the top perversity. And then there are 2 middle perversities, the lower middle and the upper middle. Now the lower middle is, zero. I mean, you can't really divide by 2 because then at the odd numbers you don't get integers. So the best you can do is you can either say, I start with 0, 0, 1, 1, 2, 2, and so on, or it's not entirely canonical, or you could say that the best I could, the best approximation to the real middle is either this or this. Right. So this is called the lower middle perversity, and this the upper middle. Okay, so these are rather important. Also, we have the following terminology. P and Q are complementary, or sometimes also called dual, if pk plus qk is the top perversity, so k minus 2 for all k. So you can see that, for example, the 0 perversity is dual to the top perversity, and you can also see that the lower middle and the upper middle are dual or complementary to each other. Now, using this, we make the following definition. We define intersection chains in degree I for such a perversity P now. So you fix a perversity, and we define a chain complex depending on that perversity by saying take all I chains, and now we modify the condition we placed on the transverse chains by, as we said, allowing a certain deviation from I minus k. So we say now that the dimension of the intersection of Xi with a stratum of codimension k is at most I minus k, but now I allow myself an error of p, and that error is specified by the perversity and given, so what you plug in is the codimension. So these k's here, always you should think of them as having the interpretation of the codimension of a stratum, right? Now, in order for this to be a chain complex, I need to specify a similar condition on the boundary. So we do that. We require this also for the boundary. And I say this should be less than or equal I minus 1 minus k plus pk. So then this is a chain complex, and the intersection homology is the homology of that chain complex. So you get lots of groups, right? I mean, if there are lots of strata, and then you can choose a lot of perversities here, and so for each one of them you get these groups, and so you have a very, very large spectrum of groups here that you associate to a singular space. So let me make some side remarks. We could, of course, do everything with finite chains. We could do everything with finite chains. So in other words, we would use a chain complex in general for a PL space consisting of finite simplicial chains, and then whose homology is the ordinary simplicial homology, and then use that here and specify the exact same condition, and this would then give us intersection homology with finite chains, which I'll write like this. Second remark. There is a little subtlety here, which is the following. Actually, for ordinary homology, can be computed from a fixed triangulation. You don't actually have to go through this co-limit, right? If you have a basic course on algebraic topology, you say you have a simplicial complex. The fixed simplicial complex has a homology, and so then that's actually independent of how you triangulate the space, right? So you can, so this is actually not true, unfortunately, for intersection homology, and so we really have to do this. So that's a little kind of a subtlety, although one can analyze exactly what one can say about fixed triangulations. And so the remark then is the following. So this is not generally true, not generally possible for intersection homology. However, that being said, the following is true. It can be computed from so-called flag-like triangulations. So if your triangulation satisfies a specific condition, then you can use a fixed triangulation to compute intersection homology. And flag-like means that so suppose this is a stratum, xi. Now, whenever you have a simplex, that simplex should intersect a stratum at most in one face, right? And so here in this picture, it intersects it in two different faces. So this would not be flag-like, not flag-like. But of course, you can always repair this, because if it isn't flag-like to begin with, then you simply subdivide it, right? You subdivide. And now it is flag-like, right? Because now you have that intersects it. This intersects the stratum only in this edge. This one intersects the stratum only in one edge. This one only, and so forth, right? So it's now flag-like, although it hasn't been before. So you can always make it flag-like if you want to, and then you can compute from that fixed flag-like triangulation. So these are just some technical remarks on actually how to compute these, but that's of course important in practice if you actually want to compute something. So in that sense, you don't really ultimately have to compute with the co-limit itself, if you like. Now, perhaps for the problem session, maybe you could think about how one could introduce relative intersection homology groups. So you should think about for which pairs this would make sense and so on. It has to fit into a long exact sequence of a pair, of course, whatever you do. So maybe you can think about this a little bit, right? How would so you know for ordinary homology how you define relative groups, but now what would one have to do here to have relative groups? So they are not defined for all pairs of subspaces. So you have to think a little bit, what is a good class perhaps where you can do it and so on. So that's perhaps something we can talk about in the problem session. Okay, now that we have these groups, what are some of their properties? Well, first of all, as I said, you get a factorization of this inclusion map, because whenever a perversity P is less than Q, then the inclusion induces a chain map from ICP to ICQ, which in turn induces a map on homology. So you get canonical maps like this. And so then the picture that we sketched earlier now becomes the following. On one end of the spectrum sits cohomology. Now you immediately apply cap product with the fundamental class, and then you land in intersection homology with a zero perversity. And from this, you can go on to higher perversities, and so on. There are all these groups now sitting in between here, as we said. Finally, of course, you get to the top perversity. And if you don't place any restriction at all, you go to homology. So the map that is being considered initially for Poincare duality, cap product with the fundamental class, is now seen to factor like this through many groups, and you can stepwise analyze where actually one of these maps fails to be an isomorphism and so on. So you have a very detailed scheme of understanding where Poincare duality fails. And as we said, McCrory says that this is an isomorphism if X is normal. And similarly, by the way, one can show that this is an isomorphism when X is normal. So there's really no difference between the top perversity intersection homology and ordinary homology. Now the main property, however, is the following, and that's of course a theorem due to Goreski and MacPherson. The main goal was to restore Poincare duality. So of course, which form does Poincare duality take now? So the main theorem, I would say, about this is there is an intersection pairing but we have to be careful about the perversities. The main thing is, I mean, if X were a manifold, we could just write ordinary homology here, and then this would be the Lefschetz theory. But now we have to be careful about what to put here, here, and here. So if this is some perversity P and this is some perversity Q here, and you want to land in perversity R, let's say, then you need to have in general P plus Q is less than or equal R. Okay, so you could put P plus Q there if that's a perversity. And furthermore then, if we are in the complementary case, in other words, if we now take P here, so let's now say that these are in fact complementary, and I take classes with respect to perversity P, and then chains in degree n minus I, cycles in degree n minus I for this dual Q. Well, so then I land in the top perversity. For 0, right? And maybe I'll use real coefficients now. So then this form is non-degenerate. This is a bilinear form now, and the theorem says this is non-degenerate. Sorry?
This is a general pairing which may be degenerate, right? Or is
Yeah. I mean, here, no. This is right. Here, I'm making no statement about degeneracy. Right. Yes. Right. Right. Only right. Mm-hmm. Yeah. And a third property that one should mention, perhaps already, is. The other main theorem is that these groups are in fact topological invariants. So in particular, independent of the stratification. Which is not at all apparent, right? Because the definition depends heavily on your choice of stratification. And then you take homology, and then the groups themselves, the homology groups themselves, do not depend on how you stratify this. So the proof of this is not entirely easy. You have to sort of use intrinsic stratifications and so forth. But this I will not discuss further in my course. But I want to prove ultimately this. But I don't want to prove it with PL chains, which could be done in an elementary way. But elementary, right, that always means difficult, right? It's elementary, but usually it's very tricky and difficult. It's what I want to do instead is I want to build up more machinery, use sheaf theory, and then the proof will come out in a very elegant fashion using sheaf theoretic methods. Yeah. No. So that's a complicated question, which we could also discuss in the problem session. So it's a very good question. When does a continuous map induce a map between intersection homology groups? So it's in general false, right? Because if you take any chain and you push it forward, it need not satisfy these conditions anymore if you take an arbitrary map. Now you could of course analyze that and see what kind of condition do I need on the map so that the condition does remain satisfied in the target. And if you do that, then you're led to what's called placid maps. So there are induced maps for these so-called placid maps. In fact, for the problem session, you may want to think about this. What condition would I have to place on a PL map, let's say, so that it does induce a map on intersection chains. I mean, the conditions are all on the board. You just have to think a little bit, what do I have to assume, right? Also, there is a class of maps called normally non-singular maps. Perhaps when we come to sheaf theory, I'll say more about this later. And in fact, normally non-singular maps also induce maps on intersection homology groups. But maybe I'll talk about those later. But it's a good question. Yeah? But it's in general not a functor. It's also not a homotopy invariant. And I think later today we'll see that. I mean, even in the compact setting, it's not a homotopy invariant. You may, of course, say, well, but you are using Borel-Moore chains, and you just told us anyway that that's not even for manifolds, that's not a homotopy invariant, so that's not a big surprise. But that's not what I mean. I mean, even for compact spaces, if you use, right, or if you use finite chains, even then intersection homology is not a homotopy invariant. It's of course clear that it can't satisfy all of the Eilenberg-Steenrod axioms, because if it did, it would be ordinary homology, which doesn't satisfy Poincare duality. So it's of course necessary that some of the Eilenberg-Steenrod axioms must fail. And so, for example, what fails is homotopy equivalence, homotopy invariance.
What does this mean exactly, topological invariance?
This means that a homeomorphism of topological spaces induces an isomorphism of intersection homology groups.
No matter what triangulation you use.
Right. It's, yeah. And it's not so, as I say, it's not so easy to prove. Yeah? But one has to use the intrinsic stratification. And basically, if you have two different stratifications, you want to compare both to the intrinsic one. And
Homeomorphisms are always placid maps.
well, I mean, yeah, I mean that's rather special, right? A homeomorphism, yeah. I mean, it's. Okay, so we will focus on the duality and not so much on this theorem in this course. So let's see. What is responsible for the singularities in a space are, of course, these normal cones, as we discussed, right? Therefore, to really understand what's going on in intersection homology, I mean, let's try to do some computations, perhaps. Before we do, actually, I have another suggestion for you for the problem session in the context of McCrory's theorem. So here, perhaps, also for the problem session, that's a good exercise. Discuss the necessity of the normality condition in McCrory's theorem. And perhaps do it for the pinched torus. So this is extremely simple, right? There, as I pointed out, the normality condition is violated. So perhaps you could try to compute for this very, very simple space what the intersection homology actually is and compare it to the ordinary cohomology and then see, perhaps this shows the necessity, right, of the normality condition. We'll see in the problem session. But so I want to devote some time to the cone now, because the behavior of intersection homology on the cone essentially controls everything. Because then I just have to cross with Euclidean spaces. That's no big deal. That's easy to trace what happens there. And then you have, in fact, Mayer-Vietoris sequences for intersection homology groups with respect to open subsets. And so it follows from this that essentially the behavior is controlled on cones. So that's a key thing that one has to understand. So let's talk about the cone to some extent. So let xk minus 1 be a compact oriented pseudomanifold, PL of course. And I want to consider the cone on X. And I would like to understand what is the intersection homology for perversity P of that open cone. Now, it should be clear how the cone is to be stratified. If X is stratified, then you just take cones on the strata and take these to be the strata of the cone. And finally, you say also that the zero stratum of the cone should be the cone point itself. So I'll write C for the cone point here. All right, so the cone point should be, of course, if there's a stratum here, then the strata will go in like this, but then the cone point itself must be an additional stratum because it has a different link, right? The link of this is actually X itself, so it needs to be stratified as its own stratum.
And the top 1 times the X should also be a separate space, right?
But I take the open cone.
Oh.
So the boundary is not actually there. So maybe I should draw it like this, right? So this denotes open cone here.
But the origin, I mean the cone point is also not part of the open cone, right?
It is. So what I call open cone, so the definition of this is...
Zero closed and one open.
Yes, right. And then at zero.
But if you close at 1, then you just get the strata of X.
Well, if you close here, you don't get a pseudomanifold. I then have a problem
Not a pseudomanifold.
because I then have this kind of boundary which I wanted to exclude and which I sort of have explicitly included excluded from my definition. So that's you're right. Then it's a little bit. One has to be careful. So one has to distinguish two cases. Let's say I is greater than k minus pk. So in this case, suppose that Xi is an intersection chain of dimension I in the cone. And suppose it's in fact a cycle, so that it represents a homology class. Well, what is the condition? The condition is, after all, that this intersection, and now I'm going to focus on 0 here. This should be less than or equal I minus k plus pk. But this number is now negative, so it means Xi misses the cone point. So the picture would be, so here's our open cone, and here you have this PL chain, but it does not go, and it has no boundary actually, it's a cycle, but it's not allowed by these conditions to pass through that point. But since Xi is simplicial with respect to some locally finite triangulation of the cone, it means that there actually exists an open neighborhood of the cone point such that the support of Xi is actually contained in the complement. So it really stays away. It cannot come arbitrarily close to the cone point even. It must stay a definite distance away from the cone point. And therefore, in other words, the support of Xi is contained in some interval. Maybe I'll write it like this. So here is 0, and here is sort of t naught, and then it's out here. Or I guess I want to really write it like this. So it's contained in there. But now we have won the game, because if you know that the chain sort of here it's infinite, right? Here it's non-compact, but if you can cut it off like this, if it lies in a region like that and has no boundary, then you can just do the following. So for example, I mean, there is a technique in PL topology which is called combing sometimes. So you can just do the following. If the value of the chain here, say, is 17, right? So you stratify. Of course, this is just an interval. So you can triangulate it nicely, maybe like this, and then you simply assign 17 to all of these, and you just keep going. And then this is the boundary of that thing. And if you do this for all the simplices, you will get a chain whose boundary the given cycle is. And so this shows that Xi is the boundary of some eta. And in fact, that eta is also allowable. Anyway, it stays away from the cone point, so there's no problem, right? It goes to the other side. So this would be the eta, right? So eta is an intersection chain, one dimension higher, with the same perversity on the cone, but actually supported in that region. And so therefore, the intersection homology is 0 of the cone in that range. So we conclude the intersection homology, perversity P, for such I vanishes. So let us consider the other case then. So I take again some intersection chain. On the cone, and I might as well already assume that the boundary of that chain is the cone on something. Let's call that alpha. Alpha is an intersection chain. I guess in degree I minus 2. Right. And the claim that I want to make now is, what I want to show is that every Xi can be written as the cone on some other intersection chain. Now that can of course not literally be true. it can only be true up to a boundary. So what I want to claim is that I can write Xi as a cone on some gamma up to a boundary. For suitable gamma and beta intersection chains. So how do we see this? So maybe it's a good idea to make a picture. So I know that the boundary is the cone on something. So here's X. And then there's sort of a chain here, right? So that's in that region. That's my Xi. Now here's the boundary of Xi, which I know to be the cone on some alpha. So here, well, maybe I should use color. So here is so here's alpha, and then you take the cone on alpha, and that's the boundary of your Xi. So now the argument runs as follows. Well, again, this chain is simplicial with respect to some locally finite triangulation of this cone. So if I go really close, epsilon, if I go sufficiently close to that cone point, the chain is guaranteed to look like the cone on something, right? So let me call, if I go in epsilon here, let me call this region N. That's a sort of, or N epsilon. That's a small epsilon neighborhood of the cone. So I know that the given chain over such a neighborhood must certainly look like the cone on something. And since the chain itself satisfies the intersection chain condition, so does this chain, because it is Xi. So, so we have that. Let me perhaps call this Xi C for Xi near the cone point, sufficiently close to the cone point. So the gamma, of course, which is a chain in X, must have as its boundary the alpha. Right? So here's the gamma in the picture. Well, I guess I'm here. So you can intersect here and you see the alpha here, and then the Xi, and then the gamma is this orange interval. And so you know that the chain here looks like the cone on that gamma, and the boundary of the gamma is exactly the alpha, right? Okay, and now I consider the difference. The rest I claim is a cycle. So why is it a cycle? Well, if I compute its boundary, the boundary of Xi is the cone on this alpha, and near the cone point, the chain looks like the cone on gamma. So that boundary is cone boundary gamma, and boundary gamma, however, this is alpha, and so it's 0. And so this difference is a cycle, but it's also contained in a definite region as before, away from the cone point. So the same argument that we made previously applies now to say that since this is a cycle and contained away in a region away from the cone point, it is the boundary of something else. So there exists, therefore, a beta so that this difference is the boundary of beta. And so then we have proven the claim, right? Because now Xi is written like this. And so what we have shown is, so we have shown that if I look at the intersection homology in degree I minus 1 with perversity P of X, and I want to compare it with the ith intersection homology of the cone, then if I take Xi, I can cone the chain to get a chain in here. And then under this assumption, this is well defined. In fact, if I is exactly equal at the cutoff case, if I is exactly equal to k minus pk, this map coning will actually be well defined only on cycles. Then you need the boundary of this to vanish. But this is fine if I only want to consider it as a map on homology. So I'm not saying that there exists a chain map from IC I minus 1 to this, because if Xi has a boundary in the cutoff degree exactly at I equal k minus pk, there would then be a problem. You couldn't do this. But for cycles, it's okay. And so we have shown that this is an isomorphism, right? Because I have shown that up to a boundary, every intersection chain can be written as the cone of something, so comes from here. So this computes, this settles the case of the cone, right? So let me summarize what we know now. So we have a complete understanding of the cone.
Would you think of this part as basically the analog of suspension isomorphism? I mean, if you kind of think of Borel-Moore, you're sort of modding out the boundary, right? So this looks...
Yeah. I mean, so the following is true. Right, so as you say, there's also a suspension isomorphism. Because if you have, in fact, any chain, let's first take any chain, I minus 1 chain on X, and you want to compute the Borel-Moore homology of R cross X, then there is a similar map, as you say. You could take a chain here and send it to R cross Xi in here. And this induces a map on homology, and this map is an isomorphism. And this is called the suspension isomorphism in Borel-Moore homology. So this computes the Borel-Moore homology of R cross X. So you can return to our example. If you take X to be a point, right, then H1 of R is H0 of a point, which is Z, right? So again, this matches up nicely with the example that we had earlier. And you can do, in fact, the same. A little calculation shows that if you do this with intersection chains, then it works the same way. So therefore, I mean, if a chain is P allowable in X, then R cross the chain is P allowable in R cross X. And so if you cross with R, then the intersection homology of that product is computed like this. And so altogether then, you could in fact compute the intersection homology now, combining what we did for the cone with this. You could compute now the intersection homology of any distinguished neighborhood. Right? So we understand it locally everywhere now for a pseudo-manifold, and then in principle you understand it everywhere, even globally, by Mayer-Vietoris arguments. So, so I wanted to summarize here what we know so far. How do you compute the intersection homology of a cone? Well, it's 0 when I is greater than k minus pk, and it is IH I minus 1 p of x when I is less than or equal that number. So that is a fundamental fact about intersection homology of a cone. We could then again take up our side remark from earlier again and talk about finite chains. If you want to, if instead you took, by the way, finite chains on your open cone, then if you did the same calculation, of course some of the internal arguments will change, of course, because this combing technique doesn't apply anymore because it generates an infinite chain and not a finite one. So you have to do it differently. But it's not too hard to see with finite chains that what you get is 0 if I is less than, I guess, k minus 1 minus pk. And now there can, of course, not be a degree shift if you use finite chains. And so you have something like this. So let me check this. Yes. So let me see. I less than k minus pk. So I guess I wrote it wrong, right? It's like this. So it turns around. I guess I just wrote the sign. I mean, you should have seen it from this. It comes from this condition, of course. I guess I just wrote it wrong. So I want that this is negative. So I less than k minus pk. So you have this. And so you should write, okay, sorry. So you should write this. It gets turned around. Sorry. Yeah, I mean, it should have been clear here that I wrote it the other way. Anyway, right? So that's the correct statement. All right. So that now we have a certain degree of understanding for intersection homology, and now I want to go on to discuss what Cheeger did to some extent, or at least I would like to look at the cone and look at L2 cohomology of the cone with the kind of metric, with the kind of conical metric that Jeff Cheeger considers. So I want to discuss next, and especially I want to compare these results with results about L2 cohomology of a cone. Yeah?
In the last line, should it also be the intersection homology of I minus 1?
No, because if you use, I mean, here, of course, it should be finite, right? But if you use finite chains, there is no degree shift. For example, here, you can already see this here. If you use finite chains, of course, this space is homotopy equivalent to X itself. Therefore, for ordinary homology, since that's a homotopy invariant, this must be isomorphic without a degree shift, right? If you use finite chains, that's a homotopy invariant. So there's no degree shift here, and then correspondingly, there's no degree shift here. So it really must be IHI. All right. So Jigger's L2 cohomology of punctured metric cones. So let me take a manifold, a Riemannian manifold. I want no boundary, but it's not necessarily compact. And everything will be oriented. Maybe I won't say it anymore. I'll say it one last time. Everything is always oriented here. So, I mean, in Jochen's talks, we use the notation lambda, little lambda of m. But perhaps since I only want to consider in this argument, the way I'm going to say it, a smooth L2 forms, so maybe I'll use it. It's maybe better to use a different notation for that. So perhaps I'll just write omega I on M for the smooth differential I forms on M. And now recall, we've already seen this, a form is L2 if, when you integrate omega wedge star omega, so here this is the Hodge star on M, which we've already discussed in great detail, if this is finite. Or another way to say it is we could look at the norm squared of omega and integrate it against the volume form. It's the same thing. So this should be finite. So then we call it L2. Now, I'll write omega 2 for these kind of smooth L2 forms. But I'll use this notation for forms which satisfy this even for whose D also satisfies this. Because then this is a chain complex now, so I can take its cohomology, and that's the definition of H2. So now H2 of M, I'm going to define as here as the ith cohomology of that complex. Okay, and now we consider a special type of M, namely a punctured metric cone. So this is the following thing. So punctured means I take the open, so, okay, x, let me now say xn is a compact, in fact, a closed-oriented manifold with a metric gx. So a closed Riemannian manifold oriented, of course. And you take the open cone on it, but then immediately you remove the singularity. You remove the cone point. Of course, that's just a silly way of writing a product, right? So this is nothing else, of course, but an interval 0, 1 cross x. Let me call the standard coordinate on 0, 1 r, and local coordinates here x1 through xn. And then the cone point sits at r equals 0. So that is a punctured cone. Now what about the metric? Now we equip this with a certain kind of metric as follows. So Cheeger considers the metric so I'll write PMC for punctured metric cone. The following metric on this space, you take dr squared plus r squared and the metric on x. Right? So it really looks like an actual cone the way you were used to. So then a punctured metric cone is such a pair. So the cone point deleted with this kind of metric. So this would be an M, such as before. And we want to compute, again, we want to understand the cohomology of this cone, but now the L2 cohomology of this punctured metric cone on X. So we want to, this is what we want to understand ultimately. So it seems that I'm almost out of time, so perhaps it's not worthwhile to start sort of the actual computation here now. I guess I'll do that perhaps next time. But there is, of course, by the way, from this a projection to x, pi, and this induces a map on forms and you want to understand that map first. In other words, this space is compact, so I might as well write a 2 here. So the first question we shall have to investigate in order to understand this is question, does pi star restrict to a map into L2 forms? I might as well write 2 here, but this is of course the same since X is compact. Now this is not always the case, but it's true in a certain range of degrees. And then eventually what I will prove next time is that in that range of degrees where this restricts, it will then induce an isomorphism, so that if we compare it with this result, we get exactly that case for intersection homology. And then a similar argument will show that above that range, in the rest of the degrees, this group is 0. And this corresponds to the second case here, so that this is very suggestive, right? So that we see that essentially L2 cohomology of a cone with that metric is dual to this. And that is sort of what we will see at the beginning then of the next lecture. Okay, thank you. Are there any questions that you might have?
So is there a correspondence between Cheeger's L2 cohomology and the usual L2 cohomology?
What do you mean usual L2 cohomology?
Because now we use smooth forms that are L2, and usual L2 cohomology use the closure in the L2 norm, smooth form.
No, it's supposed to be the same, yeah.
It
take the closure, not the closure actually here, you take the maximal closure of D. That's the difference. I will explain this tomorrow, I guess.
Yeah, so of course these groups depend on the metric, but only up to quasi-isometry. So if you change the metric up to quasi-isometry, nothing happens. But otherwise, the groups depend strongly, of course, on the metric. So. Okay, thanks.